because it's the gravitational pull. That's the conservative force we're dealing with here. So negative integral big G, mass 1, mass 2, over x squared dx.
Yeah. Okay.
I guess I'm mixing my x's and r's here, so I guess make officially x is the distance to here, from Ri to R now.
Oh, okay.
Big G and the two masses are constant, so I can just pull them out. And so I'm left with negative big G, mass 1, mass 2, integral of x to the negative 2 dx from some initial distance to a final distance.
Yeah.
And what is the antiderivative of x to the negative 2?
Would it just be x to the, no wait, don't tell me.
Nah, because it's in the bottom, isn't it the...
It is a power
X
rule.
to the negative 1, negative x to the negative 1.
So this becomes G, mass 1, mass 2, over x from Ri to R now.
Really?
The negative that you get from the integral cancels out with that negative.
Oh, never mind.
Oh, it does make sense.
But I thought I was thinking about how it was ln something when it's less than, when it's negative.
Oh, if it's x to the negative 1, then natural log would have popped in.
Okay, cool. That's nice to remember, actually.
All right, let me take a pause here because we got a negative sign in the wrong place. Where did I
Negative
do that?
sign in the wrong place. Well, oh, because it became -1, so then we got a negative, negative. So we would move it all over a negative.
Didn't see anything wrong.
Are you sure you can take those negatives cancel out?
Yeah, because you can just pull it out of it. And
The integral of x to the negative 2 dx is negative 1 over x.
Yeah.
that's what we have.
So then,
Oh, it's 1 over it.
yeah, and that's what I was saying. Does
Does it have something to do with the constant? Just spitballing.
No. All right, so I'm integrating from some smaller to some larger value. Dx is definitely in the direction that you're going in, from smaller to larger. The force is on mass 2, is back towards the planet.
If you switch the intervals, you switch the sign. Is that what it
Yeah, that
hear me out.
affects other things.
That's
I'm gonna take a
really
small little
1 over
limit right
x
here
squared.
and figure out where my minus sign is stuff.
If we have a negative in front of 1 over x squared, it's
Oh,
just negative 1 over x squared, right?
Yeah.
So you can't cancel them out,
We have not made a mistake.
right?
All right. So I have this difference right here for the amount of work it took. Now last time we talked about the fact that my total work is equal to the change in kinetic energy. That's what we did last Thursday. And in the video. It's one of the work energy relationships. If I'm dealing with non-conservative work, why do you suppose it's called non-conservative?
doesn't not traditionally make sense. Caveman talk.
Not traditional.
Maybe
What is not
it
conservative?
changes. Like it's not constant, so it's not conserved.
What is not constant?
The work? The
No,
work
not
is
the
a
work.
one number? Oh, okay.
You don't store up work, you use all your work.
The energy.
Work is a transfer of
Energy.
energy. So we're dealing with energy. So non-conservative work does not conserve energy, so that work is equal to the change in energy.
Oh.
So we did a hand wave there on that. And energy, well, I've got kinetic plus potential. My total work, well, I have only two types really. I have conservative and non-conservative. So my total work should be my conservative work plus my non-conservative work. So if we combine these two equations, non-conservative work is just my total minus my conservative. work total minus work conservative, is equal to my change in kinetic energy, which is just my total work, plus delta U. I end up with a conservative work is equal to the negative change in potential energy. So what I have on the board here are the three work energy relationships. The first one is known as the work energy theorem, but all three of them are the three work energy relationships, which we'll use and exploit.
So what is conservative work?
The formal definition is that the amount of work done is path independent. So if I take an object, let's say I take the marker and I throw it up into the air, when it gets back to where it started, is there any change in the kinetic energy? If the change in kinetic energy is 0 when it goes through the full path, then the force that was exerted on it is conservative force. So in that case, gravitational force. So if I throw an object up in the air and it comes back to where it started, if there's no resistance, no friction, anything like that, the speed is the same.
And that would be conservative?
And that's a conservative force.
Because it started, it didn't,
But since it fell to the ground, it's not a conservative force.
But still is, the conservative force definition depends upon if it comes back, one way of looking at it is if it comes back to the same starting point.
Oh, okay, if it goes back there.
Yeah.
Okay.
but the idea is that the energy, which way it came up with, it comes back down with?
Yeah, the total energy stays the same. So it starts out as all kinetic, it starts out as kinetic, that kinetic, so if this is my kinetic and my potential over here. As the kinetic decreases, the potential increases, and then it starts falling back down, so the
Does conserving the energy?
Yeah, because potential energy is like stored. And then like if you move, then it like decreases
That's why it's
the potential energy.
So what would be an example of non-conservative?
friction.
Friction.
Because friction is always opposing the direction of motion. If I had something that underwent friction that somehow went there and back, friction, the total friction would be negative because it's opposite the direction of movement the entire time.
Oh.
Friction is a classic non-conservative.
That makes sense.
Normal force, also non-conservative. Pretty much, well, everything except for those two so far. Both actually being really special on that. Everything except that one from what we've done so far.
That makes sense. That clarified a lot.
All right, so we have this formula over there. This is the work done by this conservative force. And for the most part, I'm just asking you to trust that that's a conservative force. This is my conservative work. And based upon this, that should be equal to the negative change in potential energy, which is negative of U final minus U initial, which is just negative U final plus U initial. So the question is, what is a formula for this potential energy which will make this true? I have this is equal to this. What is a formula for U that would satisfy this equation?
What is a formula for you to satisfy that formula?
The change in U is equal to U final minus.
Change is always final minus initial.
Right. WC equals negative change in U. We have a change in U. Oh. Is that the one?
All right,
Can we
let's look back up here for a second. If I had 5x final minus 5x initial is equal to U final minus U initial. If I had that equation,
5x.
what would be an equation for U that would make this work?
5x.
Yeah. So in this case, U is equal to 5x would work. There are others, but
Oh.
so down here, I have this GM1 M2 over R final minus GM1 M2 over R initial is equal to negative U final plus U initial. So what is a formula for U?
Wouldn't it just be GM1 M2 over R?
If I did that, this is not correct.
No.
If that's it, then this would become negative G M1 M2 over R final plus G M1 M2 over R initial, and that's not what we have here.
Is it?
Oh, so it's just negative GM1 M2 over R. Okay, that makes sense.
What is another formula that would also work? There are an infinite number of formulas.
Oh, great.
R times, in parentheses, G M1 M2 to the negative 1?
Oh.
Sorry.
You're just manipulating this
Yeah.
one thing here?
Yeah.
Negative
Yes,
1/2
you can
R.
express this in other ways, but I'm thinking something
So
that
not
is
negative.
not just these moved up and down with a negative exponent.
Oh. You just
Could also
scale.
just 1 over R times G
Can't
M1.
really scale.
Just like put a 2 on both sides.
Oh, 2 on top and bottom? Or 2 there and 2 here?
Negative 1/2 R times GM1.
Alright, let's tackle this slightly differently.
Yeah. This is new for all of us.
Yeah.
I have a planet here.
Okay.
A radius, we'll just make it 100,000 meters. It's a large planet. Oh, no, small planet. I'm not here. 5 times that distance, obviously not to scale, 500,000.
Here to here, 100.
Let's make this mass 5 times 10 to the 12th, and make this mass 3 times 10 to the 4th. I'm going to say that potential energy in this spot right here is 0. What is the potential energy here? Let's make it visual. 0 joules.
Oh, it's in joules?
Yes.
Okay. Would you use, okay, so,
We're trying to figure out what the potential energy would be there.
What's the potential energy at the surface of this planet if the potential energy there is 0? And I will say,
It can't be 0, can it?
it can't be.
is it?
Or whatever. There's a way to do it.
It is, because I just said it was.
Oh.
That's a key hint there, that's 0 there,
So it's moving?
because I say so.
Because.
I'll make sure to put that on the test.
That's right,
Yeah,
Biz.
there are times. We've dealt with that before, why is I hat positive to the right? Well, because somebody said so.
Right. Right.
Can you apply this to other answers?
I tried.
It can be applied to other answers, however,
But what would the potential
if
energy?
you do it, you can't do it anytime there's another answer.
So if I filled that out on the test, it wouldn't really.
They probably would not happen.
Well, we got both for mass, and we have
Maybe a couple extra points.
All right, if I plug into this formula, I think
We can figure out what that other one is, but I don't know off the top of my head.
all right, I'm gonna plug into this formula here, and so I get negative 6.67 times 10 to the negative 11th times mass 1, 5 times 10 to the 12th times mass 2, 3 times 10 to the 4th, divided by the distance of 500,000. Someone be kind enough.
Not saying it's gonna be right, but I'll get you an answer.
That's a negative at the very beginning, right?
Yes, it is. So I'll take care of that part. Negative.
I got negative 20.01 technically.
Yes.
Oh, you're not nicer than I expected. Units?
Joules.
Yep. Obviously, it's not 0. So there's something wrong with our equation.
Negative.
Or there's something I did to the equation.
It's the object's moving.
No, that have to be.
Is it just moving in the opposite direction?
It's not an issue with the movement.
Did we confuse, because we're assuming that that's zero, the a planet from afar?
I said the potential energy at that point is zero. And let's be more specific, gravitational potential energy. I'm not doing some, hey, there's energy you don't know about.
In a force, is this somehow related to like a force diagram? There's another force.
No,
No. There's something we're missing.
it's so incredibly simple that you're overlooking it.
Yeah.
Calc students are usually too sophisticated.
Aren't all of us calc students?
He's trying to make physics students.
The 100,000 from the flat.
That's kind
That's
of
not happening.
Center to center.
Calc all day.
All right, so let's try it a little bit differently.
That's two.
That's
Yeah.
two.
Yeah.
No trick question. Tell me something else that would work.
It's like, what are
Five.
the units?
Pardon?
-5 plus 7.
No. And if we did
Like,
5
what-
minus
9
that,
minus 7.
would still be 2.
11 minus 9.
1 plus 1.
69
looking
minus
for a difference
67.
Okay.
What you say?
10 and 9.
69 minus 67.
There was another one that was said, but I'm hoping that there's if I said that this was our starting point, how are these changing?
The
Oh,
overall
that's
change
like
is the same.
it's the final minus the initial. Keep going. And then that's the final. So we need to find the initial. No. Because isn't the change, isn't the potential energy is going to come out to 0.
At that point. Because I said so.
Right.
So
If you had been up here, you could have come up with a different number.
So we put 0 on the right side of the equals, and then we put -20 joules in to the difference part of the equation.
Is it,
Except that -20 is not a difference.
did we put the numbers in the wrong order? No?
I don't think so.
Like they should, like, there's nothing with our math that's wrong that's making it come negative?
No,
Okay.
that's not the issue.
Okay.
No, this way.
No square.
Alright, we're dying to know.
Yeah, we are.
Apparently we're
Is it
done.
anything math related?
Yes, very much. Let's think about what we actually solved when we were doing this. This right here is a difference.
Yeah.
Right.
This right here, I can change it around so it's UI minus UF,
That's the difference.
is a difference.
Yeah.
Okay. And all of those are also
If
different.
that added up to 2, that could be 7 and 5 or 9 and 7 or whatever you
Okay.
end up with.
But it adds up to 0.
Let's not go there yet. Let's drop back. I'm dropping back here. What is, and I'm going to use the word difference as in what is difference, not as in the math term difference. What is the difference between this and this?
The starting and ending point?
The change of the numbers is both 2 in that instance.
And here,
2.
Technically 2. For the next one, it would be a change of 1.
you're here.
Yeah.
So if I change this by each of them by the same amount,
Yeah.
does that change the difference?
No.
No. The constant.
The equation of this, all we know is that the difference here is equal to the difference here. This does work, where the constant is 0, but there are an infinite number of constants we could pick. So when you're dealing with potential energy, any of the potential energy formulas, there's always a constant that is either understood or you're given enough information to find it.
Okay.
So the potential energy at this point is anything I say it is, because I can define that constant to be anything I want it to be.
Okay.
But once I defined it at one place, I've now set it for my problem.
Okay. So we can do the math for that one to figure out a constant, and then we do that constant on the other thing?
Yeah. So this constant would be, since I went 0 here and I got that, the constant here would be 20.01 joules. And so so now I recognize that my formula for this problem is negative big G mass 1 mass 2 over R plus 20.01.
Oh. Because it makes up for the, oh, okay.
And this becomes incredibly useful because when you start solving a problem, where you choose the potential energy to be 0 is up to you. Because what we really care about is the change. We don't care about what the actual value is as much as the change in potential energy. And that is apparently where we're leaving it today. So I guess we have the test on Wednesday. And Thanksgiving next week.
Is there a pile of papers?
Is there a pile of papers? I have lots of piles of papers.
Pile of papers for master set.
That was crazy.
Oh, the hanging in? No stacking to this. At the moment. Okay.
That was
There's now a stack.
As far as the corrections go,
We should have gone with constant. There's always a plus.
Dude, yeah, we knew how to do a basic integral. But no,
He made us forget about the one thing
Yeah,
that you're not supposed to forget
should be on
about.
separate paper.
I would always forget to
I know, to add a constant.
And what you're trying to do is convince me that you understand the problem. So just putting an answer down.
It's like,
If you watch the video
first you learn to
from
do angular
class,
derivatives, you just do.
whenever I handed the test back, I think it was last Wednesday, there's a video partly in there where I talk about what's expected.
Dr. Fox, I have a question.
Let me,
Did
let's
you-
go ahead and kill this.
Oh, sorry.